We have to wait, yeah, the projector until the lights is away. He will come. Can you find him? It's about to start. All right. Good afternoon, everyone. So it seems we are ready to start, and I'm happy to welcome our first speaker of our section of scientific computing infrastructure. Now, our first speaker is Alexander Safonenko. He will present online. Alexander, could you please share your screen?
Yes, hello.
Hello, I can hear you. Yes, perfect. We can see.
Can I start?
Yes, you have 15 minutes for the speech and 5 minutes for the discussion.
Okay. Good afternoon.
Can you be heard, Rudolph? Yes. Now we see your slides. Now it's good.
Okay. Good afternoon. It's a pleasure to present my work. This work is about algorithm for traffic flow planning in software-defined networks. This algorithm is based on ant-colony optimization. So traditional computer networks are not the best for current quality of service requirements. So there is software-defined networking that solves the problems, and it separates the network control plane from the data plane. So the network control plane is a virtual graph where we can centralized construct passes, and then these passes we will pass to data plane. So I'm interested in control plane because I want to develop algorithm for constructing passes. The network is represented by a direct graph. Each edge has a delay, bandwidth, packet loss probability. A road from one node to another is represented as a path of nodes. Also, will be several classes of flows. The first one is mice flow. It's a small by size flow that is highly sensitive to delay. The second one is elephant flow, which one is big by size flow that require large bandwidth demand. So we have to separate them, otherwise there can be conflicts. For example, elephant flow can occupy most of the available bandwidth of the edge, and mice flows will experience increased delay. The problem is formulated as a minimization of several functions. Functions can have conflicts between each other. Like for these functions, I decided to take three of them. It's delay of the path, risk of the path, and bottleneck remaining bandwidth of the path. After minimization, we will get lots of solutions, and to get the best one, we will use Pareto optimal, so we will get non-dominated solutions. So in result, we will get passes that are low by delay, low by risk, and high by bottleneck remaining bandwidth of the path. There are lots of already lots of algorithms for this task, for this problem, but I will let's see the four of them. First one is the classic Dijkstra algorithm with delay as edge weight. The next one is multi-objective Dijkstra that has already more optimized routing metrics, but they go to the weighted sum. The next one is Tsaka that is based on end colony optimization algorithm. It has division into classes, but it doesn't have multi-objective optimization. And Motlaq also is based on ant colony optimization algorithm. It has no division into classes, but has multi-objective optimization, Pareto optimal. So the proposed method Paca combines two routing strategies. The first one is deterministic algorithm for mice flows, and the second one is multi-objective ACO based for elephant flows. The motivation is to preserve low latency for mice flows and to select routes for elephant flows to to avoid conflicts between these two type of flows. So for mass flows, there will be a classic Dex algorithm with delay and risk as the edge weight. This choice provides low latency and low risk. And also, Dijkstra algorithm is computational complexity is low, so it also a good one for mass flows. For elephant flows routing, it's too a bit more complicated. So there is a plan. Firstly, we have initialization of pheromones, then ants, then pass construction by ants, then pass evaluations that were constructed, then archive updating, then pheromone update, and it go to another to second iteration from point 2 to point 5, and after that we will get final road selection. So firstly, as I've already said, I give every edge of the graph a constant value of pheromone, and also I compute a delay based Dijkstra pass. So delay based Dijkstra pass. So the search, and also I give additional pheromone value to every edge of this path. So the search doesn't start from a completely uniform pheromone distribution, but receives a meaningful initial direction. After initialization, the ant colony constructs multiple candidate passes and construct passes by selecting next node to go. The probability depends on pheromone value tau. It's this pheromone, as I've already said, is initialized was and also there is and also when ant goes through this edge, it leaves some more pheromone. So next ant will choose this node with more probability because there are more pheromones. And the next one is heuristic desirability, and we'll choose it from the set of valid neighbors of node I. And heuristic desirability is the next one. So ant will choose node with low delay, with low risk, with high remaining remaining bandwidth of bottleneck, and also with low distance from the next node to the destination node. The last one was added to prevent algorithm to build along road, along paths around the whole graph. Okay, next, when we got passes, we will evaluate them by three functions I've mentioned earlier, and we will add them to archive of solutions. After that, we will use Pareto optimal to this archive, so only non-dominated passes will remain. If the number of stored solutions exceeds the archive size, the crowding distance is used to preserve diversity among the stored passes. After that, every edge of graph will get pheromone of operation with the parameter rho, and also every edge of the path of the archived roads will get the next value. Also, if the current archive contains too few distinct roads, the algorithm interprets this situation as a lost exploration. So in this case, a row will be higher. And also, to prevent premature convergence, the pheromone values are bounded. After the search phase, after all iterations, we will get final archive passes, final archive, and we will take from that both high quality and sufficient different from each other roads. And then we will distribute elephant flow proportionally among these chosen passes. For simulation model, simulation model was implemented in Python. Each graph link has a delay, bandwidth, packet loss probability, current load, and utilization, where utilization is current load divided by bandwidth. Example you can see on the figure. Also, delay and packet loss are dynamic values, and they depend on utilization. Traffic is generated as a sequence of flows. So here you can see start and end node, required flow throughput, flow duration in steps, and flow class, so elephant or mice. For experiment scenario, I decided to choose graph with 100 nodes, 50 steps, 50 new flows per each step, and probability of an elephant flow is 20%. As a performance metrics, I chose the next one. First is blocked flow ratio. When algorithm constructed the path, if the path doesn't meet bandwidth requirements, then it will be blocked. So blocked flow ratio is the number of blocked flows divided by the whole number of flows. Block demand ratio is the same, but we talk about not the number of blocked flows, but the number of blocked required flow throughput. The next one is average delay for all flows in 5% of worst in worst 5% of cases. The next one's the same, but only for mice flows. Then expected packet delivery ratio, also for worst 5% of cases. Runtime, max link utilization in the whole graph. Congestion time is number of steps when max link utilization was more than 900 more than 90%, divided by the whole number of steps, and Jane's fairness index. So as you can see, by flow blocking and demand blocking, Dijkstra algorithms, Tsaka, Motlak, Tvaka are better than Dijkstra algorithms. The three other columns only show information for non-blocked flows. So as you can see, for example, in the third column, Dijkstra has better results for delay rather than, for example, Tvaka. But it can be explained that Dijkstra just block a lot of flows. But in the mice, we can see that Tvaka is the same like Dijkstra, which is very important because mice flows are highly sensitive to delay. And by PDR, we can see that Tvaka are better than Tsaka and Matlak, but worse than Dijkstra. It also can be explained because Dijkstra just block lots of flows. By congestion, Tvaka shows the best results, and by Jane index, Tvaka shows the best results with Tsaka. So we can see that Tvaka uses lots of edges and passes in the network, not just several of them, and try to overload them. No. So in the result, we can say that Dijkstra algorithms show high level of flow blocking. Tsaka and Matlak reduce this flow blocking, but they has a high delay or high runtime. Tvaka ensures a low flow blocking with lower latency compared to Tsaka and Matlak. Thank you for your attention.
Alexander, thank you very much for your talk. So please, questions from the audience? Please.
Should I go or just ask it?
Probably. Alexander, can you hear the question if...
Hello.
Not good enough, but yes.
Yeah, maybe you can try to come up to that microphone.
So now it's better?
Yes.
Okay, so the question is, the heuristic algorithms is always about exploration or exploitation. In your algorithm, could you control that balance? And also, would it work good if we have a large graph but low number of agents?
Well, if we have a large graph but low number of edges, I suppose it will be work worse because it will try to find better passes, but it will be hard because elephant flows are very big by size. As it was said in one article, elephant flows is like 10% of all traffics, but it has 90% of the whole throughput. So I suppose that it will just took all the bandwidth of the edges, so mice will experience a high delay. So but it can be solved. But maybe it can be solved the next way that we as I do in my algorithm, split elephant flow in different, and we send it by portions. But then elephant flows will have very large delay, but mice flows will be low.
Okay.
Okay. Are there more questions? I have a small question. So what is the scalability possibilities of your algorithm? So it seems it has this centralized nature, especially with this pheromone storage. So how would it behave in its current form if we have like millions of nodes? Will it scale well, or you need to do some modifications?
Well, I suppose if we have lots of nodes and lots of edges, of course, in real world, I suppose you mean, so it will work bad, it will work good, but I don't know how good it will be. Maybe this time that it has will be too big for mice flows, or for elephant flows, I meant. So maybe we can play with parameters of the algorithm to make it lower. Yeah, and of course we have to play with parameters of algorithm because current parameters, I said, they for 100 nodes, and for different kind of nodes, millions will be another one.
Yeah, so since we can expect that the runtime will be high, but the results, the metrics will still be good. And my
Yes.
suggestion for the future work, you should try to look into the decentralization of the algorithm. So try to suggest some ideas how we can split this algorithm, this work to different nodes without this common knowledge, and maybe it will help also shortening the runtime for large scales.
Okay, thank you.
If we have no more questions, then let's thank the speaker again. Thank you, Alexander.
Thank you.
Thank you, and we continue with our next talk by Evgeny Batulin. So Evgeny is here in person. So let's welcome Evgeny. Please come here, and we'll have your presentation ready. So this one is sharing, right? Okay. So the audience online, can you see the slides?
Yeah.
Okay, and we can choose. All right, Evgeny, welcome.
Okay, thank you. So, good afternoon, everyone. And the work I'm presenting today is multi-layer computing systems. And first, when we think about why would we even use multi-layer computing systems, we would go from the classical one-layer architectures, and go beyond that in the distributed computing systems. So why would we need that? First of all, when we talk about distributed computing systems, they are really difficult. And the problem could be very variable, especially when we talk about precision of the management or how we manage those systems on the scale. Especially if you talk about the delays or computational power or scalability of those systems, we can see that the larger the system becomes, the less we could control it, and the more we lose our efficient power, which we can see in our system. So the goal of this work is to maybe find a way to evaluate new approaches and find the new possibilities to decrease those losses. So to start with, we could go for related works, especially we could see what are current trends and current challenges in the field to get the idea of what we are looking for and what type of distributed system we are working with. So if you look at this graph, we can see that there are many different approaches and many different trends today, especially all know about artificial intelligence. But here I want to point out more about multi-cloud systems and hybrid cloud strategies. And maybe we could talk about edge computing and fog computing because it will emerge inside the topic. And lastly, we can also see this green cloud idea, but if we look the inside of it, we can see that the idea of efficient processors are not about optimizing for environment. It's more about we can produce more computational power with the less overhead. So the idea here is not about the environment. And if we look at those trends, we can see some challenges which emerge from those, especially if we're talking about resource optimization. If the system grows, we can see that our use of the resources is not efficient. We lost some computational power, and we are looking to improve this. Next one is data security. Here we are not talking about this one, but this is also relevant if you can see. And some things like dynamic heterogeneity and dynamic workload organization, which is also a part of the resource allocation and optimization. So I briefly could explain how we do this research. It was made by looking at some papers which were like large explanations of current cloud approaches and how we manage them. And about like 30 papers we were in, and we searched for keywords, searched for some other statistical things that could help us, and we get the representation that could help organize our research. So if we're looking for idea to optimize our resource allocation and management of the systems, we need some kind of technology. So the technology I propose, which could be useful for us, is resource virtualization, which could help us to work with the heterogeneity, and logical virtualization, which helps us with the management problem, which we will describe later. So in the resource virtualization, we have like two main technologies: is virtual machines and containers. Probably I shouldn't talk about much about them. And the logical virtualization comes from system architecture or system design. Those approaches helps us to organize our system in better ways. And with those two ideas, like adapter and plugin, we could build an architecture which could be better and adaptable in the runtime. So, and also there is a hierarchy, as I told it, is my paper name. There are multi-layer computing systems, and the idea here is to use logical decomposition and technical decomposition to get the idea how we independ or keep the system in some reasonable layers. But those technologies mostly rely on functional blocks for logical decomposition or technological concerns like storage or computation for technical decomposition. And here we could propose a new way or new metric, manageability, which is representation of how many nodes or how well we can manage system on the scale. And I will show you the idea about in the next slide. So here is the famous Gustafson's law, which represents the system scaling, and also I added overhead, and you can see that the more nodes in the system, the larger the overhead is. And the idea here is we should decompose our system right before the overhead is start to increase exponentially. So pretty simple. And here is why we introduce this concept. It's pretty simple how we could reduce overhead. We should reduce the latency, if it's possible, with the physical resources, or we should reduce the number of communications. Here on the image, you can see famous internet scaling law, which is quadratic, and if you add some nodes, the communication will grow exponentially. So the core strategy is to use some resource-independent representations, which sounds a bit strange, and I will try to explain it in a simple representation. So when we working with the scaling model, most of the time we think of the single task when we got Amdahl's laws, or we are talking about the volume increase when we get Gustafsson law. But how do we even get the idea that computation goes in the total sum? And so you can see, right? When we talk about single task, we have some synchronization, which adds up the computational power. But if you have two absolutely independent systems, they work independently, but could we organize them without adding connection or adding even single connection to make them work on the same task? Here is the idea of management scalability. So we searching for some point that removing the communication would not destroy our system, but we still working on the same representation on the same task, or even we could talk about not the same task, but more like the way we are approaching or doing it is goes closer with our idea. I think the simplest representation of it is like when we use the neural network, we have an API and computation for matrices. And there are two independent tasks, but if we look at the whole system, we can see that it solves only one problem. So computation power is combined. And I would like to represent it with some idea of how manageable the system is. To do that, I used some sigmoid function and some magical numbers, which comes from communication overhead law or binary law. And you can see that there is some exponential decrease in manageability, and with this representation, you can clearly see the point when we need to split our system. So here's the discussion. First of all, there are many examples which are running in the world right now, which are applied and used heavily. So I would represent one example when we talk about iterative learning, we have the problem of heterogeneity of resources, and even without losing the computational power, we can see that this system relies on multi-layer architecture. So this shows us that we not only optimize for latency, as I showed with the Gustafsson law, but also we can split the system based on our internal rules. And so in this work, we mostly examine the idea of computation scalability and how we could approach that. And our central recommendation is to find an appropriate metrics which can clearly define or identify the manageability scaling point where you could split your system. And so for future work, we are asking those questions. First one is there a general approach to search for manageability split point? As I told, it's not like related to some kind of one metrics and depends on the system. Also, what is the metric we should aim at? Because performance loss, as we talk about like classical scaling, is not sufficient. And the last one is would we apply those laws to collaborative research? Because to validate this model, we could not easily run it on local PC or even some small cluster. We need some collaboration with the organizations to run it and verify the results. So thank you for your attention.
Thank you, Evgeny. Please, questions from the audience? Do I have questions? Do we have questions from the online audience, maybe? Okay, I have a question. So could you please go back to this, I think, 2 slides before conclusions? Yes, this one. So as I understand, you now propose like this more theoretical framework, conceptual framework, how we can make adaptive hierarchy of distributed system. So my question is exactly, so what would be the appropriate metrics? Maybe some examples, simple examples for different systems. So if you can illustrate what could be the metric, how we can evaluate it, and what would be the final decision then?
Okay, so we done it with federated learning. Here we have some kind of device reliability. But let me also make another example with the storage systems. In the storage systems, we could have like general storage, or we could split it in the fast, slow, and medium layer. And the optimization metrics would be request latency for user and the cost of the storage for balance. So we optimize that point, and manageability point comes from the optimization of it. So we want the best experience for user with the less cost for our system. Well, hope that's answered it.
So it seems that you are searching for kind of Pareto frontier, depending on the balance of requirements and what the system can do. Like you want the fastest results, whatever it costs in terms of energy or money, or you want to save your money and energy and you don't care about the speed. So this kind of requests also affect your solution, the architecture of the system.
Yeah, I think here I presented the like general concept for optimization tasks, and in the like defined system or the system you apply into it will emerge some different optimization tasks, and you should choose the right metrics to solve this.
Okay, thank you. Yes, please.
Sorry, did you try it with some specific problem, or it still remain theoretically?
More like theoretically, but there are some communication with the organizations we want to apply the system to. That's, if you know probably you don't know about Joint Institute of Nuclear Research. We are trying to collaborate with they have some supercomputers to run like real large system, because I could not evaluate this approach on like my laptop or like university cluster, because we have like 10 nodes inside of it. And in the future work, I hope I could get to like real computational power and validate those results.
Okay, are there more questions? No questions online? Okay, then let's thank you again. Thank you. And let's try to proceed to our next talk by Alexei Chernigov. But I was warned he has some technical difficulties. Alexei, can you hear us? I need to unshare this one. Alexei, can you hear us? Do you have difficulties? Maybe we can skip this talk and go to the next one if Yue-chan is ready. Yue, are you ready?
Can you hear me?
Yes, we can hear you. Are you ready to present now?
Yeah.
Okay, so I suggest that now you start, and then we go back to the talk that we skipped at the moment. So you please share your screen.
Wait a minute.
Yes.
Can you see my screen?
We can see your browser. Yes. So if you can show your slides.
No, actually, I have already opened the slides.
No, we don't see the slides. We only see your browser with our Jitsi room. Yes,
can you see?
now it's better.
Okay.
Can you try to change the slides, please, now?
Sorry, I can hear you.
Can you change the slides now? We will just check that you see they're moving. Can you show the second slide? Yes, it works. Okay.
Thank
you. The floor is yours. Thank you.
Hi, everyone. So my name is Jiang Yue from St. Petersburg University. Today, I will present our paper on the behavior of Pate on the class imbalance and non-ID data. So our paper investigates whether the teacher voting mechanism of Pate remains stable when federated data are both class imbalance and non-ID. And in Pate, multiple teachers models are independently trained by different subsets of private data, and their predictions are later combined through voting. The motivations come from two common characteristics of federated financial data. The first one is class imbalance, where minority class samples are limited, and non-ID partitioning, where different participants receive different data distributions. And therefore, Pate depends not only on accuracy of individual teachers, but also on whether they can produce sufficiently large voting margins. So the Pate voting process is shown here. When a query sample is given, each teacher predicts a class, and the predictions are aggregated into a vote histogram. And Gaussian differential privacy noise is then added to the vote counts, and the class with the highest noise vote is released. And therefore, the vote margins directly determines how likely the added noise is to change the final prediction. And in class imbalance data, minority class samples are limited from the beginning. After directly the non-ID partitioning, these minority samples are not evenly assigned to every teacher. If the total amount of data is fixed and the numbers of teachers increases, each teacher receives less local data, and some teachers may receive too few minority classes samples, so they cannot learn a stable decision boundary for the minority class. And therefore, increasing the numbers of teachers does not necessarily make pattern more stable, and in some imbalance and non-ID settings, more teachers may simply means more teachers with insufficient data, which reduce the voting margin for the minority class. And here we first consider whether each teacher receives enough minority class samples. If a teacher has enough minority class samples, we treat it as a qualified teacher, and otherwise it is treated as an unqualified teacher. Under an optimistic assumptions, qualified teachers correctly vote for minority class, and while unqualified teachers vote for the majority class. And in this way, the voting margin depends on the numbers of qualified teachers. The results in the figures show that under several severe class imbalance and directly partitioning, as the numbers of teachers increases, the expected vote margin does not increase. Instead, it decreases and even becomes negative. And the dashed lines represent Gaussian noise threshold. If the voting margin is below the noise threshold, the aggregation's result can not reliably resist the noise. And this meant that with the fixed amount of data, increasing the numbers of teachers may dilute minority classes samples and push Patet into a noise-dominated region. And in the give me some credit results, we can see that class imbalance and non-ID partitioning make Patet very sensitive to change in the numbers of teachers. The left figures compare AUC on the different teacher counts. DPSGD remains around 0.64 to 0.69, while Patet is generally lower, roughly between 0.31 and 0.55. And more importantly, Patet does not improve steadily as the numbers of teachers increases in some settings. For example, 10 teachers perform better than 30 or 50 teachers, maybe. And the right figures gives possible explanations. When the numbers of teachers increase from 10 to 30 and 50, the blind teacher ratios rises from about 0.07 to about 0.28, and then remains around 0.27. And this is consistent with the previous vote margin analysis. With fixed data volumes and severe class imbalance, more teachers may split minority class samples into smaller parts, so voting signal does not necessarily become stronger. And next, we further examine whether the failure regions of Patek can be identified in advance under different data conditions. And several public tabular data are used, covering different data sizes, features counts, and minority class ratios. And this allows us to observe how Patet behave under different tabular data conditions. And the screening experiment used 16 random seeds. If the student model's AUC is below 0.7 under any seeds for configurations, that configurations is treated as a failure. And so based on the previous failure mode, our paper proposed a pre-training screening strategy. The goal is to judge whether data conditions and parameter configurations may be suitable for Patet before spending the actual private budget. So this specific approach is to simulate the basic conditions of real data, such as sample size, minority class ratio, and feature dimension, and then adjust the classification difficulty. Let's make it possible to observe where Patet may fail without directly using the real data at this stage. And two indicators are used. The first one is S, as is the average cosine similarity between teacher data distributions, which describe the consistency among teacher partitions. And the second one is sigma divided by n, which measures the noise strength relative to the numbers of teachers. And a large values means that the noise is stronger relative to the voting signals. And finally, configurations are grouped into bins according to S and the sigma divided by n. And the failure rate of each region is calculated. And this method is not intended to predict every round precisely, but to identify potentially degraded regions before training. So privacy budget is not wasted on clearly unstable configurations. And this slide shows that the failure rates heat map for Give Me Some Credit and German Credit. The yellow regions indicate high failure risk. The failure regions are not completely random. They form continuously structures over the S and the sigma divided by n bins. For Give Me Some Credit, the data volume is limited and the minority class ratio is low. So stable, learnable regions for Patet are almost absent. And for German credit has even smaller data volumes. Although its minority class ratio is not as low as Give Me Some Credit, it also lacks reliable, learnable regions under this setting. And this suggests that for small tablet tasks, especially when the classification signal is weak or class imbalance is strong, Patek can easily enter a degradation regions. The next one, this slide shows that the results for bank marketing and CDC diabetes. Unlike the previous slides, these two datasets have larger sample sizes, and so the heat map shows clear low failure regions. This indicates that Patet is not unstable on all tabular datasets. Its behavior depends on data volumes, class structures, partitioning, and whether teacher voting can form a sufficiently stable margin. Another important observation is that learnable regions usually appears as continuous blocks rather than scattered random points, and this means that the binning with S and sigma divided by n can reflect the applicable regions of Patet to some extent, and therefore this method helps partitioners remove obviously high-risk configurations before running Patet queries. And in summary, this work shows that the performance of Patet in federated learning is closely related to data distribution, class structures, and signal redundancy. And where minority class samples are distributed across too many teachers under deregulated partitioning, the blind teacher ratios increases and the voting margin decreases. When the voting margins fall below the Gaussian noise threshold, aggregation becomes noise dominated, and student performance also decreases. And to judge whether a configuration is suitable for Patet before training, this paper proposed a binning strategy. The experimental result shows that the failure rate heat map has continuously regional structures, so they can help distinguish potential learnable regions from degraded regions. And however, our result do not mean that the Patet is unsuitable in all scenarios. The degradations observed in this paper mainly comes from the weak tabular signals and class imbalance and non-ID partitioning. And in high-dimensional data, such as image or text, where stronger semantic redundancy may exist. So teacher voting may still be more stable. And therefore, the main conclusion is that when Patet is used in federated setting, we need to consider the relationship among data distribution, teacher partitioning, and also the differential privacy noise. Thank you for your listening.
Thank you, Yura. please, your questions. So I have a small question, you. So could
Yes.
you please go back to your slides? I see you unshared the presentation, but we will still need it. Could you please bring it back? Well, in fact, my question was about the last slide, where you have your conclusions, and you say about the large number of teachers. So the question is about scalability. So your approach is related to federated learning, and what are the numbers? So how many teachers you can have that your approach still works correctly? So can you discuss this scalability issue?
Actually, for different data set is totally different. So for some data set, it might be a success, and for another one, it could be fail. So before we start the experiment, use real data, we want to have a method like in our paper that we can use some, so we can use the data which simulate the real data to predict, to know the distributions like this. So we can
Could you
see
please
that the
zoom
distribution
into
is very close. So the probability to
zoom in?
the real data will be more possible to success.
Could you please zoom in this slide, because it's not very visible for us. So they are too tiny. So if you can just, yeah. Okay, so what are the axes there? Maybe even bigger, if you can make it even a little bit bigger.
Sorry, the voice is very slow, very low.
Okay. So what do we see there? Can you comment about the axis there? What's on X and Y axis?
So we just simulate the upper side is the simulations of the real data, and the lower side is the real data. So we use the simulated data to run the to use different parameters to run the result. So it shows that the yellow ones shows that every parameters, one of the parameters will be lower than 0.7 AUC. So we can see that in if S is around like for example these regions, and the how to say sigma over n is around from 0.04 to 0.20, it might be more possible to find the usable models, global models.
Okay, thank you, Yue.
Thank you.
Thank you. Do we have more questions? No more questions. So thank you again. Okay, so let's try to check if Alexei could solve his problems. Alexei, can you hear us? Check. Okay, I think the problems have not been solved yet. So I suggest that we can go to the next talk. And I see the speaker, Tran Dukman. Can you hear us?
Yes, I'm here. I'm listening.
Are you ready to present now?
Yes, I'm get ready.
I suggest that you take the turn, and then we go back to our previous speaker. Can you please share your screen?
Yes, I did. Can you see my screen?
No, not yet. Okay, it's coming. And yes, we can see your slides.
Okay. So I'm gonna start right now. Wait a minute.
Can you make it a bit larger? It was good before, but something changed.
Okay.
we still see it small. So now it's much better. Now it was better.
Oh, wait a minute. I'm trying to fix it.
Now we only see some small. Yeah, I think it's okay. Yeah, it's not the largest by some reason, but we can.
Oh my God.
I'll change it again. Okay, let's try. Yeah, it was.
Can I do like
Just
this?
keep it like, if you can keep it like this, then it's okay.
Okay.
Thank you.
Hi, everyone. My name is Trần Đức Mạnh, and today I will present our paper, Optimizing Harmful Information Containment in Social Networks via Shortest Path Interdiction. About motivation and problem, information can spread very fast on social networks. A fake news item may start from only a few accounts, but after that, it can move to many groups and communities. So the question is, if we have only a limited intervention budget, which nodes or links should we block? In this work, we try to reduce two things. The first one is peak infected, meaning the maximum number of affected users at one time. And the second one is total effective, meaning the total number of users affected during the whole diffusion process. Limitation of existing method. A common method is degree centrality. These methods select user with many connections. It works well when the network has large hubs, for example, very popular users or KOLs. In many closed groups, forums, or local communities, users may have similar numbers of connection, but not all social networks are hub-based. In these networks, harmful information may spread through bridge nodes between communities. Degree centrality may miss deep bridge nodes. Another method is betweener centrality. It can find bridge nodes better, but is expensive for large graph. So we need a method that can find important spreading path, but is still scalable. Objective and contribution. The goal of this study is to design an effective intervention method. We focus on networks with community structure where bridge nodes are important. Our main contribution is SPID, which means shortest path interdiction for diffusion. The idea is simple. Harmful information often spreads quickly through short paths from source nodes to target community. If we block important nodes on the short path, the diffusion becomes slower. So we also propose SPID plus. This method updates the shortest path after each intervention because the information flow may move to another path. SPID intuition. If this slide shows the main idea of SPID, on the left slide, before intervention, harmful information moves from a source community to a target community through a short path. We call this path a fast confusion corridor. If we block an important node on this corridor, the fast path is broken. After intervention, as shown on the right side, the information must use a longer path. In some cases, it cannot reach the target community easily. And problem formulation. We model the social network as a graph. Each node is a user account, and each edge is a possible information transmission link, such as flowing, sharing, or interaction. The set SO contains the init, so harmful information source. The set TO contains the target users or target communities. The diffusion process is simulated by the SEIR model, but the number of intervention is limited by the budget B. Our goal is to make the diffusion from source to target more difficult and reduce the final number in effective users. About SPID plus, SPID plus works in a simple step. First is sample some source target pairs. The second is calculate the shortest path between the pairs. First, it gives score to nodes. A node gets a high score if it appears many times on important shortest path. Then SPID plus select the node with the highest score and remove it from the graph. And after that, the shortest path may change. So SPID plus recalculates only the effective path, not on path from the beginning. This process is repeated until the budget is used. Experimental setup. We use two networks in experiment. The first one is PolitiFact from Fake News Net. This is a fake news network. It has hub-like structure. The second one is Skogaz network. This is small world network. It has many communities and shortcut links. We compare SPID plus with four methods. No intervention, random selection, degree centrality, and between centrality. For each experiment, we run the simulation 20 times and report the result. We use two main metrics, peak invertic and total invertic. Main result. The main result is on the Skogaz network. This network has strong community structure. Without intervention, the total infected value is about 1,700. With degree centrality, the value decreased by about 4%. With between centrality, the value decreased by about 8%. And with SPID plus, the value decreased by 9%. This is the best result. This shows that blocking shortest path diffusion corridor is effective in small world community networks. About budget sensitivity and runtimes. Now we look at the budgets. When the budget increases, decrease centrality improve as first, but when it's become saturated, this is because the most important hubs are selected early. After that, more selected nodes bring only small improvement. SPID plus is different. It's continued to improve because it updates the shortest path after each intervention. For runtimes, SPID plus is slower than decreases centrality because it needs a shortest path computation, but it is faster than between centrality. Network topology matter. The result shows that network structure is very important. In small worlds and networks, users have similar numbers of connections. The spread depends more on bridge nodes and short corridor between communities. In this case, SPID plus works very well. Conclusion and future work. To conclude, we propose SPID, a shortest path interdiction methods for harmful information containment. We also propose SPID plus, which updates the path after each intervention. In future work, we will study dynamic networks, incomplete source information, and distribute system. Thank you very much for your attention. And I'm happy to answer your questions.
Thank you very much. Next question, audience. Yes, please.
Hello. Thank you for your presentation. And the question is, in the graph, there are infected nodes and normal ones. How would we detect, not detect, but classify before starting the algorithm?
Okay, wait. Gonna back this slide. This one, right?
Right.
We use on other nodes as targets for evaluation. In practice, you can set TO as any specific community you want to protect, like teenager, volunteerable group. If for we depend on age, we have a higher protection, and we choose this object to set the value of nodes.
So we specify those classes by ourselves, right?
Yes.
Okay, thank you.
Yeah, so we have to know in advance which node is infected and which not, so we cannot just discover this, right?
Yes, right.
And I have a small question. Could you please go to the slide number 9, I believe?
Number 9.
With the plots. Yes, I think the previous one, yeah.
Main result.
Yeah.
Right. Okay.
Yeah, I wanted just a few more words, a few more comments about these bar charts. So it shows number of agents. The first one, peak infection count. So how many agents were infected? So can you please say a few more words about the bar charts to understand the results better?
Okay. First of all, we take two networks. They have like a small social network, and we practice like try to run this algorithm, and to find out the answer, we got degree between us and SPID, and depend on the result, we got this graph about amount of object is around is 20 times repeat this algorithm.
And so the reduction percentage is when you isolate these nodes, you block the nodes, then the infection is decreased with this amount of reduction, right?
Yeah.
Okay, thank you. No more questions? Okay, thank you again. Thank you.
Thank you all.
So let's try to move on and check again if we can hear the talk of Alexei.
Yes, 1 second.
Yes, so they try to cooperate with the colleague.
Do you hear me?
Yes, we can hear you.
Sorry, do you hear me?
Yes, we can hear you.
Hey, do you hear me?
1 second,
Yes.
sorry.
So if you can tell Alexei that we can hear him, that's good. So we have our complicated networking.
Okay, it will be in format of transmit, I think. Maybe
yes,
it will be not good, but we haven't any chance to do another variant. So let me start, if it's acceptable. Okay.
Yes, please.
My name is Alexey Chernigov, and today I want to present you our work, Average Frontier, a low-overhead multi-objective bischeduler for heterogeneous edge environments. This work was prepared with Vladimir Kolokov at St. Petersburg State University. So let me start with the motivation. When we talk about edge systems, we understand that computational work are performed in the place where tasks are generated, where data are generated. So it can be close to mobile devices or other edge nodes. So basically, very often edge environments are heterogeneous. So we have a lot of different devices with different computational speed and power consumption, and even some devices can execute some task types. And also devices are linked by different network passes with different parameters. Therefore, naturally in this edge environment, schedule problem appears. We need to distribute our workload between different devices, and when we distribute one task, it influences on completion time and active energy. So when we schedule our workload, we optimize n criteria. In this work, we evaluate makespan and active energy criteria. Makespan is time needed to complete all our tasks, and active energy is the time needed to transfer and compute, and it's energy that needed to transfer and compute how much task we need to distribute to concrete devices. So we just try to understand what count of task we will distribute if our task will be equal. So in this case, we can find an Pareto front simply and easily. And then when we find a Pareto front, we can select some point on this Pareto front based on our policy about trade-off between energy and makespan. And then we need to reconstruct this distribution into real task assignments. Like this concrete task should be executed on this concrete device, and we need to balance average complexity of our task, because we go from real task assignment space to surrogate space. So there are no one possible solution for selecting on Pareto front some points. So in this work, we just selected area ratio policy, and it is based on Pareto geometry and ideal solution. For evaluation, we developed an simulation one based on SimGrid. Why SimGrid? It's because SimGrid is really parameterized. We can change network, we can change taxonomy, we can change devices, and we can easily add some new scheduling algorithms. And we tested our algorithms on 2 test beds, a compact 3-node profile and a big 100-node profile to understand what we will see on the larger scale. And for comparison, we used some time-aware heuristics, energy-aware heuristics, mixed-aware heuristics, and meta-heuristics. So in this slide, you can see our baselines. And on this slide, you can see results of these baselines on our simulation environment and 2 test beds. And you can see that this curve are presented our algorithm and meta heuristics. By the 1 point solution, simple heuristics are presented. So you can see that our algorithm are close to the meta heuristics. But when we talk about schedulable time, we will see that meta heuristics take 100 times more time to give us some solution. So you can see on this slide that time needed for average frontier is close and comparable to simple heuristics time. And yeah, we can get some interpretable allocations in the task count space. We can give a controllable movement between time and energy-oriented regimes and give these solutions fastly, but we doesn't claim dominance on over all alternatives because meta heuristics search solutions in rich space, and we didn't claim recovery of the true global Pareto front. We just recover surrogate Pareto front, but you can see on this slide that results are really close. In conclusion, I will say that we developed an average frontier algorithm that can give a controllable transition between time-oriented and energy-oriented regimes, and time of scheduler work isn't big. So we can use it in rescheduling, but in the future we will focus on broader workload classes and topology configurations, and also we will investigate adaptive alpha selection based on the current system state, and also we will compare our results with real prototypes, with physical edge prototypes. So thank you for your attention. If you have questions, I will try to answer you, but it will be complicated. So, okay.
Thank you, Alexei. I'm not sure if you can hear us. Can you hear us?
I hear you, but not very good. So if you will go to the microphone, I think I will hear more.
We have several microphones. So is this one better?
Yeah.
This one is better. Ah, okay. You can hear us. Okay, so we can ask you some questions. Do we have questions? Oh, very good. We have many questions. Okay, please, lady, first.
Hello, thank you for your presentation. Can you hear me?
Yeah, I hear you.
Yeah. Okay, my question is that maybe I didn't see the constraints. Is it possible to use like exact method like epsilon constraint to calculate Pareto count even for small instances?
Can you repeat?
Is it possible to use exact method like you use the meta heuristic? Is it possible to use exact method like epsilon constraints if you have mathematical model? I don't know if you have linear constraints or not.
I think I will understand you, but maybe not. You can repeat the question later. Okay.
Okay.
So yeah, if we have meta heuristics, yeah, we can find solution with linear. If we add some linear constants, we can find solution in real systems, but it also will be really really expensive, because these meta-heuristics are based on some genetic algorithms, and maybe, as we all know, genetic algorithms are really are not clever. They are just try some solutions and then goes between and then they try to select these solutions. So maybe I will answer you, but if not, you can repeat your question.
Yes, that's it. Thank you.
Okay.
Next question, please.
So hello, you have the second objective called makespan, and the scheduling algorithm is using the sometime to computate the point where we send our batch, right? And does the time goes to that objective or it's independent?
We have when we talk about makespan active energy, we try to schedule our tasks to optimize these criteria. So this is we need to optimize it. So it's not bounds. It's our purpose to optimize, and so we just need to minimize this. But we, because we have conflicted criteria, we will we can only get some non-dominated Pareto front. But on this non-dominated Pareto front, we need to select some solution, because if I will give you a set of solutions and you don't know how to select it, you will be you will don't give me money, I think, if I will give you this algorithm.
So does the finding optimal solution counts as the execution time for the task, for the batch?
This solution calculates time to execute, and it's calculate. This solution calculates transfer time, and we need to optimize this sum. This summarize. Yeah.
Okay, thank you.
Okay, do we have more questions from online? Apparently no more questions, so thank you again, Alexey. Thank you. And I believe this is the last talk in this session. Yes, this is the last talk in this session, so we can conclude, but we meet after the break to continue with the next part. Thank you, everyone.
Thank you.
Hello, everyone. So we will start in a couple of minutes. Let's check if you can hear us and we can hear you. So our first speaker is Alexander. Alexander, can we check your sound? I'm not sure we can hear you. Maybe on our side.
Do you hear me right now?
Okay, we can hear you.
Yeah, that's
very good.
From my side. Thank you.
Yes. So I think we are ready to start. So I'm happy to announce our next section, Scientific Computing Infrastructure Workshop. And our first speaker is Alexander Shogolev. Alexander, welcome. So could you please share your slides? And you can start when you are ready. Yes, we don't hear you because your microphone is muted.
I hope the slides are showed up, right?
Yes, we can see your
Great.
slides and we can hear you.
That's really great. So let's proceed with the presentation. So the development of passport system as a mechanism of identification began in Europe around in 14th century when trading and other jobs required human identification. So personal so-called road documents contained information about the person who had these documents. Its name, his name, eye color, hair color, nose form, and other crucial details. However, we refused to use such full description in favor of photo. However, the absence of child's photo in the birth certificate allows criminals to use fake information to illegally move the child to another country, which creates serious risks for their security. So this is why it is important to create new form of the birth certificate, which contains not only documentary but also graphical and biometrical information. Also, this certificate should be available in digital form. Since a border crossing has been always connected to checking a large amount of documents and and sometimes big portions of information, it is needed to this process needed to be sped up. And one of the obvious ways is to use barcodes. For their use, barcodes should be comfortable to read and write data of digital, symbol, and character types. Also, barcodes should have a maximum size. And according to these requirements, the most suitable color QR code will be suitable because which is an RGB QR code. Each layer of it has some QR code with an information. And of course, to do such birth certificate, you can on the slide you can see the presented documentary and graphical information which is used to form a digital birth certificate. Name, year, which is also can be seen in the usual or usable birth certificate. However, according to the state standard, face image should have a size of 320 by 240 and maximum size of the QR code is 177 by 177. So to use them, it is needed to double the size of QR code and add stripes of specific size to the face image. To form a bio QR code, which will be used by parents, the color face image of the child is divided on three color components: red, green, and blue. Green component is substituted by the documentary QR code. And as you can see, the scheme of forming bio-QR codes is shown on the slide at the right. Here on this slide, you can see the examples of digital birth certificates for 2 years, 5 years, and 9 years. And please note that every certificate contains child's photo according to his current age. Since component green in bio-QR code is replaced with documentary QR code, combination of the components will give incorrect face image. So to recover the face image component green is replaced with an average of the sum of layers red and blue. Images with recovered green layer is shown on the slide at the right. To ensure that nobody cannot forge image and the documentary information about child, it is needed to store the information inside photo. This information we can place in LSB layers. To form these layers, subsequent division by modulo 2 is performed and the result is subtracted from the original image. The preparation of information for embedding QR codes into LSB layers of a color face image consists of describing its phenotype, forming documentary information, and constructing corresponding QR codes. Then these barcodes are then embedded into the LSB layers of the color face image. Here on the slide, you can see the process of writing information about the child based on embedding QR codes in LSB layers of color image of a face for storing them in the databases of government departments, for example, of Russia. However, to prevent straight access to the crucial data located in the QR codes, which are located in the LSB layers of the image, the prepared messages for QR codes with documentary or biometrical information are encrypted with the AES encryption algorithm, which allows to use keys with different lengths. And then generated QR codes with encrypted information are transformed using geometric transformation, matrix transformation, and rotations. In conclusion, should be noted that suggested new format of certificate of birth certificate contains all required information to identify the child, with using bio or such certificates like BioQR code or, for example, animated file, which consisted of images with child growth and their parents. Also, embedding information as encrypted QR codes in LSB layers of colored child face image prevents criminals to easily access that such crucial data. And of course, the new document format developed taking into account modern technologies and security requirements will simplify the identification process and ensure maximum protection of the interests of children and their parents. So thank you for your attention. Please, you can proceed with questions.
Thank you, Alexander. So please, questions from the audience? Yes, we have one question, please.
Mhm.
Hello, thank you for your
Greetings. Yes.
presentation.
Thank you.
So the question is there a limit how much information you can put in the QR code? It would be fun to have like my passport inside of it or my driving license. So could I do it?
I will refer to the one of my co-authors, Professor Kukharev's article, which quotes, quoting, which the BioQR codes allows us to replace such documents as passports, visas, driving licenses, since they have storing amount around several thousands of symbols. So it is easily to it is easily to create a passport or a driving license.
Okay, thank you.
And I have a small question. So as I understand, when you started, you showed that you can embed the image into QR code, right? So your
QR
approach
code
is both ways. But when you started, you had some images of QR codes and there was like a photograph embedded inside, or it was always the idea of embedding.
You mean the QR code?
There was something before. So you always embed QR code into image, right?
Yes, indeed.
And this QR code also contains information about the image itself. Is it like this?
It contains this.
This, yeah, like.
Yes, it can
like
be
the green one here. So it looks like you map the image onto QR code.
Yes, of course, it can be read, and it contains biometrical or documentary information. So since this is a birth certificate, it has documentary information about where the child studies, or if he is in the kindergarten, or also can be, for example, if requested, there is also can be added the biometric information.
And you say that this information is like hidden, so it's encrypted.
Yes.
But what is the restriction of making this information publicly shown? So why cannot we just print it in the birth certificate aligned with the photograph? So how can it help additionally hide this information inside the photograph instead of having it publicly printed?
As I was as I was performing later, we store encrypted information in the government databases, so they are privately secured there. But for BioQR codes, there's only information to identify the child. So here we can so in BioQR code we write the information which is used. Hold on, sorry. Here, like documentary, which is also used in the birth certificate, and the educational institution is also can be added, but some biometric data is since it's crucial information is well, it's stored in the government, also stored in the government databases, and in encryption in encrypted type.
Okay, thank you. Now I see.
Mhm.
Thank you.
Mhm.
Do we have more questions meanwhile? No more questions, so thank you again. We are ready to proceed to our next speaker. And our next speaker is, I believe, Nurjamal Kakabayeva.
Yes, I am here.
Jamal, yes, please share your screen and we are ready to listen to you carefully.
Thank you. Good afternoon, dear colleagues. My name is Nurjamal Kakabayeva. Today I'm going to present study on identifying the characteristic of brain regions in individuals with different neurocognitive characteristics based on functional MRA data. In this work, autism spectrum disorder was selected as a model of neurocognitive differences. Let me start by introducing the motivation behind study. Autism spectrum disorder is a neurodevelopmental condition characterized by deficits in social interaction and communication, as well as restricted and repetitive behaviors. The key clinical problem is that diagnosis currently relies on behavioral observation. There are no reliable objective biomarkers, and early diagnosis, which is critical for timely intervention, remains a significant challenge. In terms of research challenges, linear models are highly interpretable but do not always achieve optimal classification performance. Deep learning models, on the other hand, achieve high accuracy but function as black boxes, making it difficult to explain which connections drove the decisions. On top of that, the high dimensionality of functional MRA data significantly increases the risk of overfitting. So, the goal of our study is to develop an approach capable of detecting functional connections that are reproducible across different sample splits and exhibit high discriminative power in distinguishing individuals with autism spectrum disorder from neurotypical controls. The present study was conducted using the data from the Autism Brain Imaging Data Exchange 1 consortium. It's a large international consortium that unites 17 research centers sharing neuroimaging data for studies of autism spectrum disorder. Especially, we use resting state functional MRA data. Each file of this project is a four-dimensional array. The first three dimensions represent the spatial structure of the brain, and the fourth dimension is a time series of activity scans. In the picture, you can see a visualization of the data showing multiple time points from 0 to 150 that captures the brain's spontaneous activity during rest. The work with that data begins with pre-processing and sampling. For pre-processing, the standardized CPAC pipeline was used, which brings the data to a unified format and reduces the influence of technical differences between scanners from different research centers. Records with missing age, gender, or diagnosis values were excluded. After pre-processing, the final sample consisted of 849 patients. The data are relatively balanced between groups, but there is a notable gender imbalance. After preprocessing, we needed to extract meaningful features from the data. To achieve this, the CrackDoc 200 atlas was applied, which divides the brain into 200 functionally distinct regions. For each of these 200 regions, the average blood oxygenation level dependent signal over time was calculated. This provides a time series that reflects the activity of that region during the scan. Then, for every pair of regions, the Pearson correlation coefficient between their time series was computed. This coefficient indicated how similarly two brain regions behave over time. As a result, we got 20 by 20 connectivity matrix for each patient, where each cell represents the strength of the functional connection between two brain regions. Since the matrix is symmetric, only the lower or upper triangular part was taken. As a result, we got feature space which consists of 19,000 unique features per subject. These features indicate how similarly two different brain regions work together. Now let me walk you through our classification and model evaluation strategy. As the primary classifier logistic, we choose logistic regression with L2 regularization. It provides a good balance between performance and interpretability, which is crucial for identifying clinically meaningful biomarkers. For validation, the dataset was split into training and test sets with an 80 to 12 ratio, preserving the proportion of ACD and control participants in each subset. As a result of mapping, we found that the most significantly affected network is a default mode network. Default mode network shows pronounced hyperconnectivity because 17 connections are decreased and only 4 increased. This suggests that in autism spectrum disorder, the default mode network is weakened, which aligns with the social and self-referential deficits characteristic of the disorder. In subcortical structures, we observed the opposite pattern, hyperconnectivity with 6 connections increased and 3 decreased. This may reflect atypical sensory gating and altered processing of social stimuli. Connections in other networks appear to be less involved. To conclude, we developed a method that is not inferior in performance to more complex classifiers while being fully interpretable. We identified 22 more significant functional connections that reliably distinguish individuals with autism spectrum disorder from neurotypical controls. The neurobiological interpretation obtained after mapping onto the YO7 networks are consistent with findings reported in the literature, confirming the validity of our approach. The most significant results were observed in the default mode network, including precuneus, angular gyrus, middle temporal gyrus, and anterior cingulate cortex. These regions, which are known to be involved in social cognition and self-referential processing, showed pronounced hyperconnectivity in autism spectrum disorder compared to neurotypical controls, making them potential biomarkers for the disorder. We believe this work can serve as foundation for medical decision support systems in autism diagnosis. That's all. Thank you for listening. I'm glad to answer your questions.
Thank you, Nurjamal. It seems there was a question online from some of the online participants. So if you are here, you can ask your question directly.
Yes, I can share you. It's an open source. You can download it by yourself, or I can send you pre-processed data.
And can you read the question then again? So that was about the data.
Could you share the MRA data or the source of the MRA data? As I said, it is an open source database. Everyone can download it by himself, or I can send the data preprocessed by me.
Yes, I believe you have a reference to this data set in your paper as well. Mm-hmm. Okay, so do we have questions from the audience here in the hall? I have a small question actually also about the data set. So how general is your solution? So will it work with any MRI data set, or you have some restrictions and some requirements?
Can you repeat the question, because I didn't got it?
Yeah, the question was that you have this brain imaging data sets.
Yes.
So your method should work with any kind of MRI data, or
Yes,
it has
yes,
any
of course.
restrictions with any. So
It
it's
is
generic.
very popular nowadays to use fMRA data to analyze something, to make new decisions in diagnosing. And this method is usable for all fMRA data, not only for the people with autism spectrum disorder.
Thank you. Thank you very much. I think there are no more. Huh? Was there more question?
Yes, there is.
There is.
Presentation.
Yes, please.
A small question. What is the proportion between men and women in your research?
Proportion nearly 90 and 10%, but we have the cause why accuse this disbalance. It connect with the time when the data was collected. In this time, the female hide their symptoms, so they in this data they don't have a lot ACD diagnosis.
Thank you.
Okay, thank you again, Nurjamal. And let's proceed. And our next speaker is Viktor Koloskov. Victor, can you hear us?
Yes, I'm here.
Okay, very good. So, yes. So Nurjamal, could you please unshare your screen so that Victor could share his own? Thank you. Yes, we can see your slides. So you can start, please.
Thank you. Good afternoon. Today I will tell you about our work, multi-threaded pipeline parallelism for distributed LLM inference without source code modification. I would like to start with the fact that modern LLMs possess an enormous model size owing to the sheer number of parameters The table on the slide shows several models and their size in native format. However, contemporary GPUs are contrasted by memory limitations, requiring the model to be partitioned across multiple devices. There are two ways to partition a model. It's intralayer and interlayer. Interlayer partition is usually represented as tensor parallelism. It distributes each layer across multiple GPUs. However, it incurs frequent communication overhead, making efficiency highly sensitive to network bandwidth. Interlayer partitions is mainly represented as pipeline parallelism. A particular group of layers are assigned to each GPU that substantially reduce communication between devices. Also, many frameworks require adapting the model's source code, and today there is no efficient pipeline parallelism solution that avoids it. Therefore, the goal is to develop a concept with an efficient pipeline parallelism implementation that requires no modification of the model's source code. To partition a model without source code modification, we adapt the approach used in deep speed inference framework for tensor parallelism. The main idea is to substitute the original model's layers with parallel layers. For this, we introduce three types of layers: compute, fake, and boundary. Compute is simpler wrapper for the original layer. Fake passes computation not related to the current pipeline stage. And boundary is responsible for transmission data between pipeline stages. Naive pipeline parallelism have one significantly disadvantage. While activations are computed on one GPU, the other GPUs wait for input data. As a result, the accelerators stay idle. To solve this problem, we introduce an inference-adapted GPID schedule that enables communication overlap across pipeline stages. To implement it, we use multithreading, where each thread exclusively processes its own input data. At any given moment, exactly one thread executes computations per GPU. For the experience, we used the two configurations shown on the slide. We tested 4 models on each. The bar charts shows the ratio in throughput and peak memory for the model OPT 6.7 billion parameters. We can see that the peak speedup is 1.46, while maximum peak memory overhead is 1.08, which is mainly due to the overhead of multithreading. On this slide, we can see the results for OPT 30 billion parameters. Peak speedup is 1.42, and the maximum peak memory overhead is 1.06. It's also worth noting that at sequence lengths equal 256, speedup rises from 1.22 for OPT 6.7 billion parameters model to 1.42 for OPT 30 billion parameter model. On this slide, the bar charts show the results for encoder model in turn VIT 6 billion parameters. Peak speedup is 2.63, and we can see that it's much higher than for decoder's model. Moreover, as the number of microbatches increases, peak memory ratio drops significantly below 1.0. In conclusion, in this work, we proposed a model partition method based on layer substation, implemented multi-threaded pipeline parallelism that overlaps computation and reduces GPU idle time, and achieve up to 1.46 speedup on decoders and 2.63 on encoders with low memory overhead. Our future work will aim to evaluate at larger batch sizes and with high bandwidth interconnects, compare against optimized inference systems, and combine with other parallelism times and improve pipeline scheduling. Thank you for your attention.
Thank you, Victor. So other questions from the audience? Yes, please.
Hello, thank you for your presentation. So the question is, in your work, you described a method to parallelize the computation or distribute it. And the core idea is to use fake layers to feed the model, so you don't have to change the code, right?
Yes, but we don't feed the model. We only partition the existing model.
So in the end, models with the fake layers are, how to put it?
Yeah, it's a very good questions. Fake layers only generates output for forward pass function on the devices where current pipeline stage is not computed.
Okay, thank you.
And I have a small question. So typically when we discuss different parallel distributed systems, the question is how scalable they are. So will it work well when we have more and more nodes? So my question is, what can you say about this scalability issues or scalability possibilities? And in particular, on this slide, you have the metrics of speed up, 146 and 263. So how many nodes did you use here for these numbers, and how these numbers can change when you increase the scale of the system?
It's interesting questions. When we scale the system, it can be on the overlap of computations can be only increase if on each GPU we have enough computation time. If we haven't it, we don't the algorithm won't overlap the computations.
But I mean, so you used in your experiments 4 or 5 GPUs, right?
I use 2 GPU and 4 GPU.
2 GPUs. Okay, 2 and 4. But what happens if you use not 4 but 40 GPUs? Will your approach still work, or you need to change something?
I think it will be work. But if the model will be quite small, we don't have will not enough computation that we can overlap on other devices.
Okay. Yeah, you should always balance this computational requirements and the scale of the system. So if your model is small, then you don't need many GPUs. But if your model is large, your approach should be able to work on the larger scale systems. All right. No more questions. Victor, thank you again.
Thank you.
And let's proceed to the last talk in our section. And our speaker is Alexey Subbotin. Alexey, welcome. Can you hear us?
Yes, I'm a
We can hear you. Very good. Yes, please share your slides, and we are ready to listen to you.
Good afternoon, ladies and gentlemen. We present to your attention a report on the topic creating an operation system for video camera chips in an intelligent video surveillance system. My name is Alexey Subbotin. I am a graduate student of the St. Petersburg State Electrotechnical University. My presentation is funded by a grant of the Russian Academy of Science. The main task of an operation system is to delimit memory stack in CPU, heap in RAM, disk in hard drive, and assign access right. It can be said that the operating system is a RAM manager and utilities. Each OS executes application code with additional information contained in the header. Application headers can be in various formats. Page 0 for Mac OS, MZ for Microsoft Windows, ELF for Linux. Bytecode of different applications runs currently in the OS and should not interfere with each other. It's possible to read the RAM of all applications, but in some cases, like BSD systems, reading the memory of other applications is difficult or even impossible when having memory encryption. A goal of this task. The goal is to improve the speed of operation system for one task, the main application, and to improve the speed of loading the operation system. Main concept. The original function of all operation systems, we can see on this slide, was to redirect input-output while seamlessly performing arbitrary operations on the data. The concept of redirecting data streams from one device, the transmitter, to another, the receiver, has been preserved in all computer and operation systems. Chip in video cameras. It's difficult to impress anyone with grain size chip these days, since anyone uses bank cards and the chips on the cards in the fully fledged computers. However, a computer inside a device, for example, video camera, can significantly outperform bank chips. It may have relatively large RAM and ROM, a good processor with integrated graphical functions. Video can be processed not only in the cloud or on a fog video server, but also directly on the camera's process computer using an integrated system on board processor. Attack another processor of Access communications can be very serious, and modifications chip generations with differ its capabilities and performance depending on the functions include color correction, haze removal, night mode, clarify, brightness, and contrast adjustment, and many other features supported in explosion-proof and waterproof access video cameras. Comparison of the features and limitation of the considered OS. We can see on this slide the systems are compiled based on following capabilities: 1, 2, 3, 4, 5, and other parameters. And next, we can see on this slide the operation system are compiled based on the following features: 1, 2, 3, and next. With different two slides of with embedded systems. Вот previous slide. Problem statement of this task. Slow operation system performance for integer video surveillance systems. Program execution speed is low within the operation system, and the operation system does not start quickly on video surveillance system. We can see on this slide. After loading the file system driver, VOS checks the PC devices. A timeout device response time is specified for each device type in VOS configuration files. VOS sends an intelligent signal each time, obtains the serial and model of devices, video adapter, network card reader, etc. And check for drivers from the heap it's Linux, from disk, or if it's QNX runtime, and other. All the required drivers not found is displays on a clone device message. After launching the application, in some cases, but code in different processor. Solution method. Despite its complexity and its improved for PCs, creating an operation system is simply equivalent of the source code of the popular Minix free OS is merely as the volume of appendix in Andrew Tenenbaum book Creating Operation Systems. Samsung monitors contain with oven Tizer OS with regular updates. A few features OS can be considered as a program that provides first point, reading the binary application format. Next point, RAM manager for application collaboration. 3 point is memory management, keep stick disk with access right. And last point is support of various devices with data stream redirection, event, or interrupt pool for applications. The kernel can be monolithic as in Linux, where devices driver, memory manager, and utilities and contained in a signal file and transferred to the RAM heap at OS startup. The kernel can also be a microkernel as in QNX and contain multiple files that are loaded separately. And next, the quality of embedded technological operation system for video surveillance devices. For example, access can be improved based on following points. First point, scan devices during OS operation and not a good time. Next point, develop a RAM manager to locate the heap to a signal application. Next point is execute bytecode from an application without a translation to a specific processor architecture. Next point, optimize barcode for RAM clustering heap and the registers of a specialized processor in the device's chip, for example, video camera. And last point, emit permission access SABIC's graphical systems for this task. When graphical subsystems of a SABIC's operation system is sufficient to create a simulated console with execution of all commands and viewing video fragments from the camera flash memory. A possible implementation options for the graphical subsystem for the SABIC operation systems is an area in the browser where the data is displayed and a graphical shell with a command line developed in the form of a website using HTML and CSS 3.2 and JavaScript as the frontend and PHP with subscript as the backend. We can see on this slide on the right. Case study. Implementation of a graphical subsystem and common console in the SABIC OS. We developed over study a remote connection application for the SABIC OS. We can see on this slide on the right, which was used at the St. Petersburg State Subway, what I'm in work. SABIC OS run a web server written in C for the JCC compiler to connect to the graphical interface. Simply enter HTTP localhost SABIC in your browser and next. After conducting we can see on this slide on the center. After conducting the experiment, which the following parameters we measured. For example, P1 with good time and next P2, P3, P4 и так далее. A consumption of this all tasks. We have created an operating system adopted for video camera chips for attached video server systems. The study found that Pinac SABIC OS boots twice as fast as its computer's application launched from disk, times faster, and executing RAM times faster. In real mode, the new operation systems runs and launches application faster and no real-time time faster. According to the QNX documentation, real-time mode, the first launch application must respond with 4 milliseconds for a processor of 40 megahertz or faster. The proposed method for improving OS performance for embedded processor computers will be applied not only in video cameras for video server system, but also in other devices, smart routers, industrial controllers, and processor tablets at various stages of production and technical system maintenance. On this slide, my presentation is completed. Thanks for attention.
Thank you, Alexey. Other questions in the audience? So, Alexey, you mentioned that your system is used in metro, right?
Yes, of course. Peterburg.
Can you say a few more words about the purpose? So how it is used and what they can solve with it that they could not solve before?
We used Linux and other Unix systems, and we developed new system.
But in Metro, for what purposes do they use it in Metro? What is the scenario specific to your development?
Specific development is a special processor, for example, Axis in video camera for intelligent surveillance systems.
Okay, Alexei, thank you very much. I think we have no more questions. Thank you. And this concludes our workshop. So thank you all for participation and hope to see you next time. Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.